forgot my notes regarding today's lesson, so I'm kind of going off at the top of my head, and so there is a chance that I notationally do something incorrect, but at least I can explain the big picture part, and but regarding all of the small formulas and things like that, I might mess something up, so please be forgiving of any possible mistakes. But today I want to talk about lasso. Okay, lasso. Yeah, or slash ridge regression. Okay, and so before we get into that. So we've talked about least squares estimates, okay? So, ordinary least squares are simple linear regression, ordinary least squares regression. How are we picking the parameters of our best fit line? What's the criterion we're using? Least squares, right? But what are we want the least squares of what? Of the residuals, right? Okay, so we try to, we minimize the sum of squares residuals, okay? And so, our model is something along the lines of y is equal to x beta plus error, and then our residuals are equal to y minus y hat, and we're trying to minimize basically y minus y hat squared. So far, so good, right? Okay, and we could have, the beta matrix could have lots and lots of predictors in there, and so, but it works out, okay? And so, what the chosen beta hats at the end are known as our BLUE, which is our best linear unbiased estimator. Okay, and this is, maybe you cover this in 100B, I don't know. This is from the Gauss-Markov theorem. I don't know if this sounds familiar or not. But, even if it's not, it's that is the case of the best least unbiased of this thing. Okay, so we can all right, if we think of our parameter space, okay, so let's say we have two parameters in our model, B0 and B1, okay? Okay, so this we can graph basically the values of of this quantity, okay, the residual sum of squares, okay? So, and this would be a kind of a three-dimensional surface, right? So we would have a three-dimensional surface, and so I can represent the three-dimensional surface as kind of like contour lines. Is that okay? And so our selected b hats, b hat 0 and b hat 1, this represents basically the lowest point of what we're doing is we're graphing the residual sum of squares function. Okay, and so this represents the lowest, and then we would have basically, because it's square, you would have like these. Does this look like what I'm trying to represent here? You know what? There's actually a very good picture in Tib Shirani's book. Let me pull this up here. Okay, let me just. This is the picture I'm trying to go for that I can't do. Shoot. Okay. Let's keep going here. Ah, here it is. This is the picture. Okay, so this is the for every single we can look at all possible beta zeros and all possible beta ones, and we have this surface, right? This surface represents the residual sum of squares. So you know, if you fit another line with a different beta 0 and a different beta 1, we could calculate all of the, you know, we would have a whole bunch of different residuals, and we can calculate the sum of squares of those residuals, and it would be something else, okay? And basically, the least squares regression tries to find the spot on this surface that minimizes the residual sum of squares, okay? And so that goes right here, and then pretty much any other choice of beta 0 or beta 1 results in a higher value because this is our minimum. Okay, so this is the image that I should just copy and paste this. Okay. All right. There we go. Oh, that's not what I want. Okay. All right. So this is basically what we've been doing, or how ordinary least squares regression works. Okay. Okay. So why do we want to bother even trying to change this thing that works well for us? Okay. Well, if you have more than one, basically more than one x variable, so you have, now we have 3 predictors or something like that, then and there could be a high correlation between some of the x variables. Okay. And what happens is, if you have multiple x variables, there could be correlation, or strong correlation between the variables. Okay, and then that means the true relationship is probably y depends on both x1 and x2. Okay, so probably the truth is y depends on both x1 and x2. Okay, but just because of strange patterns in your data, okay, one data set, okay, just because of slight irregularities could reveal basically y depending strongly on x1 but not x2. Okay, and another data set could reveal y depending strongly on x2 but not x1. Yes.
So when we say y depending strongly on x1, does that mean that the beta is high or that's a significant level?
Yeah. So basically both. Okay. So it could show like, I mean, so the betas being large or small are all kind of relative, but it being large or small pretty much will impact the whether it's significant or not. Okay. Now, because of the properties of the ordinary least squares, the best linear unbiased estimator basically says, in the long run, as we average all of these different beta 1s and beta 2s that we get, we're going to get something very close to the real thing. Okay. So, in the long run, if we average all the beta 1s and beta 2s, we will get close to the true value. Okay, but in the meantime, we suffer basically high variance in our beta 1 and beta 2 estimates. Okay, but in reality, we have high variance in the beta 1 and beta 2 estimates. Okay, so we can kind of improve this, all right? And this is where lasso and ridge regression come in, okay? Basically what we're giving up is we're giving up the unbiased. We're going to basically take out the unbiased in this thing, and we're going to have a better estimator in that it reduces the amount of variance in our beta 1 and beta 2 estimates. Okay, so we'll have smaller variance in our estimates, but our estimates are no longer unbiased. Okay, so lasso and ridge regression produce estimates of beta 1 and beta 2 with smaller variances, okay, but are no longer unbiased. Okay, and so the way we do this is we apply a constraint. Okay, and so do you guys remember like Lagrange multipliers and all of that stuff? Okay, so you apply a constraint, and with the constraint you're trying to minimize. You're still trying to minimize our least squares function. Okay. Okay, so are you guys familiar with like norms of vectors and stuff? Well, just a quick brief review. Okay, so we'll talk about the L2 norm and the L1 norm. Okay, so the L2 norm, this is kind of the when you just think of the norm of a vector, this is the regular old norm. the regular. And that is basically, you know, if you've got some vector from here to here, okay, then let's say this vector represents our beta hat. So this is our value of beta 1 hat and beta 0 hat. Okay, so this is the fitted beta hat vector. So this vector represents our chosen parameter estimates. Okay, and so the L2 norm. So we would write this the norm of beta hat. We could also put a little subscript 2 to indicate that this is our L2 norm. But this is equal to the square root of basically beta 0 hat squared plus beta 1 hat squared. Okay, so it's basically the Pythagorean distance, right? All right, and we can place some kind of constraint based on well, okay, no, let's just leave that. So this is our L2 norm. The L1 norm for the same thing. Here, I should just copy this picture. Okay. The L1 norm is equal to the absolute value of beta 0 hat plus beta 1 hat. Okay, so basically this one just says how far do I have to go this way plus how far do I have to go this way. Okay, so that's the L1 norm. Okay, whereas the L2 norm is just kind of how long do we go this way. All right. Okay, and so if we think about this, if I said, if I place a constraint, okay, so if I say a constraint so that, you know, the L2 norm of beta hat is equal to some value C, what would happen? What is the where can beta 2 be equal? It's a circle, right? A circle with radius square root C. This is supposed to be a circle. Okay. With a radius equal to roots. Oh no. Yeah, root C, right? No, root equal to C squared. What am I doing? Radius is equal to C. And I think, right? Yes. Okay. All right. So anyway, yes, radius is equal to C. Sorry. All right. So that's what we have. Okay. What if I say the L1 norm of beta hat has to equal C? What do we get? So the largest it can be over here would be C, and then the largest it could be over here would be C, and then so you get this, you get a diamond shape, right? I'm really terrible at this drawing business. It's really hard drawing on a tablet, actually. I want to defend myself. Okay, So this is what we would get, okay? If the L1 norm. Okay, and this is just a two-dimensional thing, but you could imagine we can apply these in p-dimensional space too, right? So if you had beta 0, beta 1, and beta 2, you'd have a sphere, and then I don't know what the next dimensional equivalent would be, but whatever it is, okay. And then if you had over here you had beta 0, beta 1, beta 2, and you're looking at the L1 norm, you'd end up with this polyhedral thing. Okay. So just can be generalized to p-dimensional space, okay? Okay, so far are we okay? All right, so basically, ridge regression and lasso regression just apply a constraint as we are searching for our beta parameters, okay? And so let me see if I can flip back. So imagine this thing. So this is, maybe I won't do this. Okay. So for ridge regression, we have with ridge regression, we want to minimize. And let me. So we want to minimize basically our y minus our y hat. The squared residuals, okay. But then there's also we put on a constraint here, okay. And so using like a Lagrange multiplier. So these are our L2 norms, okay. So we're trying to find the beta to minimize this. So pretty much this is residual sum of squares subject to a constraint. Okay. And so in this case, we have this, and then let me copy my picture here. I'm going to just copy this part. So this represents the kind of the contour plot of what minimizes our so this is the true least squares regression estimate, and over here we've got some constraint over here that says it must be again, my terrible circle, but so we're saying, beta hats our beta must lie inside this region here, okay? Beta 1 and beta hat. Okay, and so according to ridge regression, we would pick, some spot here where we have the smallest sum of squares subject to the constraint. Okay, so this spot is the value that minimizes the sum of squares, but is still subject to our constraint. Is that okay? Okay, and so that's kind of the big picture with well, I mean that is ridge regression, not the big picture. This is just how it works. Practically, we don't try to do this ever by hand. We always just kind of throw it at the computer and say, give me the estimates subject to this constraint. Okay, and that's so ridge regression. Basically, you're subjecting it to a constraint based on the L2 norm. Okay, and so you get kind of whatever minimizes it subject to this circular zone of parameter estimates. Okay. Lasso regression, same thing, except instead of using the L2 norm, we use the L1 norm. Lasso, I should probably write out what it stands for, but I've already forgotten. Let me see. Lasso regression. All of these have some acronym. Lasso. The lasso method. It doesn't even say. It's like something. Least angle and shrinkage. Lasso and least shrinkage and selection. Okay, so nobody even knows what it's called. They call it lasso. It stands for something. Okay, but basically we are subjecting ourselves to just a slightly different constraint, y minus y hat squared, okay, L2 norm, but we're using the L1 norm here. Okay. Minimize this function. All right, and so this time we have this. Let me paste my same image here. Okay. And let me, I'm going to just try putting it over here. And then, okay. And then, so now we have basically a diamond. I can draw, oh gosh, this is really hard. Okay. All right. Okay, and so we have, you know, beta 0 and beta 1 or whatever it is. Make sure that the 0 doesn't go up there, does it? Okay, so same thing here. And what happens now? Where's our minimum point?
Choose a point that's on the contour line that's closest to 1.
Yeah, so we're subjecting ourselves to stay inside this diamond, basically, okay, or you know whatever p-dimensional shape that we have. And what we have is that with the lasso, okay, because of the shape of the diamond, we get these super sharp corners, right? Okay, and so because we have these corners, pretty much almost always, and unless you get something that's like perfectly I don't know, perfectly aligned in another way, almost always the one that minimizes the function is not going to be along this edge, but it's going to be at one of the corners, okay? Because that like juts out the most, okay? So with lasso, okay, the beta that minimizes the sum of squares, the RSS, will almost always be at the corner of the constraint. Okay, and when you're at the corner, what that means is that right here, what is the value of B0? 0. Okay, so when you're at one of these corners, one or a few of the other parameters are going to have 0 value. Okay, so at the corners, okay, one or more of the parameter estimates will be 0. Okay, and so that's kind of a nice like a nice feature of lasso regression here. Let me see if okay, yeah, okay, so I hope this explanation makes sense here regarding the lasso, and again, practically speaking, we never do it by hand, so you can just do lasso regression in R, and then there's all sorts, there's a few packages, and I'll have to look at this, but I think you can it's implemented, well, apparently there's 2 packages, glmnet and LARS, but let's see, and both of these authors are very, in terms of authors of packages, these are both very well respected authors, so you can trust both of these as being reliable for searching for the parameter estimates there. Okay, and let me think here. So I think our textbook briefly mentions the lasso, and it just says it's subject to these constraints. But that's that. I don't know. I want to give you just a little, at least a little picture of the idea behind it. Okay, and so this part here is all from the Lagrange multiplier method, right? For minimizing or maximizing subject to a constraint. Okay. Are there any questions or issues? Anything of that nature? Okay, then I guess we'll end a little bit early. We're not going to meet on Wednesday, so enjoy the rest of the week and your Thanksgiving. If you're traveling, travel safely. And I think right now the teacher evaluations are available on my UCLA, and so I appreciate you guys filling those out. They're especially important, especially because I'm a new instructor, a new lecturer. So they are very important. So I appreciate you filling those out. I hope you've enjoyed the course and enjoyed having me as your instructor. So anyway, I encourage you guys to do that. Have a great Thanksgiving. We'll see you guys next Monday.